Okay, it's a few minutes past. How about we get started? Numbers are starting to slow down. Welcome to everybody for our second webinar as part of the Ready, Set, Roman training series, which is being put on behalf of the Science Operations Center, the SOC at Space Telescope Science Institute, as well as the Science Support Center, the SSC, at IPAC. Last week, if you were able to join us, we went through an introduction to the webinar training series and walked through the user support ecosystem, explained a little bit of background about all the different tools and resources and teams at your disposal. If you didn't get a chance to look at that, everything, the slides and the presentation are now posted on our website, and I will put a link to that in the chat once I am done giving this talk. My name is Ori Fox. I am the SOC Deputy Project Scientist for Roman, and I am hosting today's session, and I will be giving you a little bit of an introduction to Roman simulation tools and data sets. And then I will pass the presentation off to Dario Fata, who is a member of the SOC here at Space Telescope Science Institute, who will give a presentation on one specific simulation tool, Roman iSim, and walk you through a hands-on notebook that will illustrate how to access existing simulations and also run new simulations. And we will talk about how you will be able to do that both now and in the future with all the tools at our disposal. Okay, so Dario, next slide. By the way, before we get started, a couple ground rules. If people want to post questions in the chat, that's probably the best way to ask questions. We do have a moderator, Vivian Yu, who is online. She just showed her camera. And she will interrupt me if something is very pressing. Otherwise, we can save the questions until the end. All right, so just up front, this is the current schedule that we have for the Ready, Set, Roman training series. We have a few more planned sessions throughout December and January. We hope and expect that there will be more sessions in the future, but these are some of the core sessions that we think you need to get started and get ready for Cycle 1 Call for Proposals, which we'll talk about in just one second. We have the QR code and the link right here. Feel free to check that out. That's where the slides and the presentation from last week are posted. You can also join our mailing list to stay informed about all future webinars and recordings as well. Next slide. All right, so here's a question of when will the Roman Cycle 1 Call for Proposals be open? I'm going to turn this over to Vivian, who is our official spokesperson on this matter. So Vivian, take it away.
All right, thanks, Ari. Can you hear me? Okay, great. So yeah, my name's Vivian Yu, and I'm the proposal team lead for Roman based at the SSC at IPAC. And I know we've gotten some questions from many folks about when the Cycle 1 call would actually be open, so I wanted to address that head on here. And so everyone knows that the release of the call was delayed due to the government shutdown, but now it's actually recently reopened. We are aiming to announce a new release day really soon, just waiting for final approvals here. But in the meantime, please feel free to check out the RTPS webpage that you'll need to use to submit your Cycle 1 proposals via that URL link here or the QR code if you prefer. And if you have any questions, please get in touch via the Roman Help Desk. So back to you, Ori.
Thanks, Vivian. Okay, next slide, Dario. Okay, so this is just a brief introduction to the data simulation tool environment or ecosystem. There are a number of different simulation tools that will be available for you to get prepared for Roman observations. And there are different tools because there are different needs. Whether you're trying to create an accurate scene or really try to understand what the underlying data look like with noise and detector artifacts and things like that. You might want to consider using real PSFs. You might really want to understand sensitivities for your specific observations. And so there are a number of different tools that will help get you there. And we have a web page that introduces these tools, which you can find at the link below. Again, we'll make all these slides available after the webinar, so you can open them up and click on the links. From this webpage, you will then be pointed to specific documentation in our documentation ecosystem called RDocs, Roman documentation, that will walk you through details about using each of these tools. We also have a specific webpage that helps you identify which tools are best for you depending on your specific science use cases. We want to point out that all tools are available for installation on your local machine using pip install generally. However, if you find that challenging or you don't like to install a lot of software on your machine or run Jupyter notebooks on your machine, creating environments, and that's a little bit intimidating to you, all of these tools will be available on the Roman Research Nexus without any additional installation required. I'm going to tell you a little bit about what the Nexus is in just a few slides. But it's basically a cloud environment ecosystem where you can run all of these tools. Okay, next slide. I mentioned RDocs. RDocs is our Roman documentation. You can see a screen grab of the website here. There are a lot of online articles focused on the user side on how to do a number of different things to work with the wide field instrument, to work on various tools such as the astronomer's proposal tool, APT, the simulation tools, and like I said, even an article on selecting which simulation tools might be most relevant for you. There's a large number of articles that are already available and many more in the works. Okay, next slide. Okay, so in addition to the tools, there are also a number of community-created simulations that are hosted by the SSC, the Science Support Center at IPAC. Among those are for the WFI, microlensing simulations and data challenges, simulations of GRISM observations, Roman high latitude imaging surveys, simulated images, NASA Open Universe 2024, Roman Rubin image simulations, and the Roman plus Gaia astrometry tool. You can find out a lot more information at this QR code and the link below. And then there's also simulations for the coronagraph. Our webinar series is focused exclusively on the WFI for now. And today we are going to specifically talk, in the demo, we are going to look at some of the simulations created by NASA Universe. Okay, so this takes me to the next slide. We Open Universe 2024 simulated Roman and Rubin images. This was a major project that went forward to simulate spatially overlapping images, surveys to be carried out by both Roman and Rubin observatories. The simulations were carried out on Argon's Theta cluster and consist of 5 different simulations, one being the LSST Elias S1 deep drilling field. The Roman time domain survey shifted to overlap with the Elias region and the LSST deep drilling field. Overlapping LSST wide fast deep survey with a rolling cadence. Overlapping Roman wide area survey in the same region, and a deep field calibration region of the Roman wide area survey in the same region. Okay, that's a lot of information. Okay, go back 1 second, Dario. Dario, go back. Yep. That's a lot of information, but there is a lot of documentation available at the link below. There's also a published paper on this. All of these data are currently available and accessible, and we're going to show you how you can do that today in our tutorial. Okay, next slide, Dario. Yeah. If you want to create your own simulations, there's a way to do that. We already talked about several of the tools. Today, the second half of the demo is going to focus on how to run Roman iSim. This is called the Roman Image Simulator. And this is a Python wrapper of Galsim that has been specifically designed around Roman's wide field instrument. Roman iSim makes use of the official calibration reference files stored in our calibration reference data system, CRDS, and the Space Telescope PSF, STPSF point spread function models. And so this simulates realistic level 1 and level 2 WFI data products. If you're hearing level 1 and level 2 for the first time, these are stages in the data processing. All the documentation online explains the different levels of processing, and hopefully in the future we'll have more information sessions on understanding these different data products. The most important thing to understand is that these are realistic data products and similar to what you would expect coming from the observatory. The best part is you can actually take these data products and run them through the Roman Cal pipeline yourself if you want to learn how to do data processing and calibration with the Roman Cal pipeline. Again, lots of extensive documentation available online. Here's the link below, and we'll be doing the demo tutorial in just a few minutes. Next slide. And finally, I promised you a discussion on the Roman Research Nexus. The Roman Research Nexus is a science ecosystem in the cloud to provide a cloud-based collaborative, and collaborative is a key word here because you're able to work with your team or collaborators in the same directory and on the same notebook or code at the same time. Collaborative computing space for the science community to explore, access, and analyze Roman's petabyte scale data. So the real point here is that you don't necessarily want to be downloading petabytes of data onto your local machine. The Roman Research Nexus makes all the data available to you at your fingertips. Furthermore, the Roman Research Nexus will include a set of tools, services, and infrastructure. So in other words, you won't have to install your own software. It will come preloaded with all the different tools, including the simulation tools that we are going to discuss today in a pre-configured environment. So you should just be able to open up the Nexus and run. Furthermore, there will be a number of different tutorials, including tutorials on simulations, data reduction, data analysis, and visualization. And these will all be pre-written notebooks, Jupyter notebooks that you can run in this environment. The final point that I want to make is that all Roman data, no matter who takes it or whose program it is, or whether it's one of the core community surveys, will be public with no proprietary period. That means that within days of the observations, you will be able to log in and access those data from the Nexus. So this is really going to be the place to do science in the future. We're going to have a full webinar on the Roman Research Nexus on January 13th. So mark that calendar, and we expect that the public release for the Nexus will occur in mid-December. No sign up is required. You just need a MyST Space Telescope ID, which you can register for at any point and log in. Next slide. Okay, so that's all I have to say today. I'm going to turn this over to Dario to start with the tutorial.
Sorry to interrupt, Ori. I was just going
Yes,
to note that there were a couple
sure.
questions in the chat. I don't know if this is a good time to kind of address them before Dario
Yeah,
goes
let's
into.
do it.
All right. So there's a question that's asked about, will there be simulations of PRISM images and Galaxy SEDs or spectra produced as part of the Open Universe simulations?
Do we have anyone on the call that can answer that? And if we don't have somebody on the call that can answer that, I will make sure to follow up with that. And we can even post some of the answers to questions on the website. But does anyone know the answer offhand from the project? Okay, we will get back to you, Gregory. That's a good question.
Okay. And then the second question is, will Roman Nexus be available free of cost to everyone, or does it come with charges?
Yes, the Nexus will be free of cost to everyone. One important caveat to this is that the Nexus is not necessarily designed to be a high performance computing center. So, to do your basic analysis, this should be sufficient. However, if you want to do more complex analysis, you may hit a limit that's imposed on each user. So each user or each team will have a certain number of credits. The details of this credit system and how to get more credits is still being worked out, but will be finalized by the time the Nexus goes public in just a few weeks. And all the details will be provided there. But to do most of the analysis, the Nexus will be free.
Thank you, Ori. That's it for now.
Great. Okay, and so I'll turn it over to Dario. Before I do, I just wanted to remind everyone that an email went out earlier this week with instructions on how to pre-install this notebook and potentially run it in advance because it does take a while to run. Dario will be going through this cell by cell. If you were running this notebook on your local machine and you do have questions, not so much troubleshooting, I don't want to debug in this session, but if you have specific questions about why certain functions were called or what certain algorithms were used or what's actually happening when a call is made, I encourage you to make this interactive. You can ask the questions in the chat and hopefully we can address these in real time. But if there's anything more substantial, we'll wait to answer those until the end. So, Dario, I'm going to turn it over to you and go for it.
Okay, thank you very much. So, as already said, I am Dario Fadda and I work at the Space Telescope Science Institute in the Roman Telescope branch. So, I have two fast slides after that. One is where you find the software. Supposedly you find it, but just in case you arrived, I don't know where it is. This is the website where this is put. And then in the case you have issues or other questions, I invite you to submit tickets to the service to the help desk of Roman, and on the desk I will stop sharing this and start sharing the. Let me just understand what it is. I start sharing the notebook, which hopefully you have. So this notebook is essentially an introduction to Roman ISIM simulations and, as already said, to how to recover images already available, simulation already available in other websites. First of all, if you don't know what I'm talking about, so I will start with few definitions. So we talk a lot about WFI. WFI is actually the wide field instrument, is the instrument that Roman will use to take images and spectra. And it's, as the word says, wide field, so it's cover almost an half square degree in one shot with 18 detectors. You see a little image here of the detectors. Roman ISIM, and it's been already introduced by Ori, is a Gaussian-based simulator that allows you to do simulation of Wi-Fi images. And this can be done at two levels, the level of 1, which is uncalibrated images, and level 2, which is calibrated images. Many other information can be found in the simulation tool handbook. So you have already heard about level 1, level 2, etc., etc. So I want to just specify a little bit more what we mean by these levels. Level 1, as I said, are uncalibrated data. So the data that comes essentially to you from WFI, and what they contain is the so-called science RAMs. So to understand a little bit what this means, you have to remember how the infrared imaging works. So when you do infrared imaging, you do reads of the detector, several reads of the detector when the image is acquired. this leads you to have, as in the little figure I added here, several reads, so which are the dots, the black dots in the figure. And as the exposure continues, we have more and more charges on the detectors, which means we have a kind of a ramp with a certain slope. This slope, when fitted, will give you a quantity which is proportional to the flux incidence on the detector. Now, since we have many pixels in this detector, and imagine for every pixel we have a lot of readings, which means it's a lot of information to send back to Earth during the observation. To reduce a little bit this information, and these reads are grouped in several groups, which are called resultants. Essentially, for any of this group, we have one single point sent back to Earth, which is one resultant. In this image, you see 9 resultants called R1, R2, R3 to R9. And you can imagine that there are different ways to group these reads. And these different ways are coded in tables, which are called the multi-accumulation tables, which I will refer later because depending on this, you can have different type of level 1 products generated by the simulations. Okay, you can have more information about all these products in the Roman documentation. I just add 2 levels, which are mentioned here, level 3 and level 4. As I say, level 1 is the ramps, level 2 is the images, so all the slopes have been calculated and put in a file. Then you can go through the Roman pipeline and put several images together to obtain a mosaic. And these mosaics are called level 3 in the jargon. And finally, you have catalog of sources that are produced also by the Roman pipeline, which are called level 4 products. Just to finish this introduction, I'll say that there are 2 notebooks that go in slightly more deep than this presentation, and they are linked here in this part of the notebook. So, as essentially said before, I will do a first part which includes the information about accessing already simulated data already available, which are typically hosted on IRSA, so the Infrared Science Archive of IPAC, and on the Roman Research Nexus that has been mentioned by Orin, will be open for use very soon. But data are already available there, so I will show how to access them. And then in the second part, I will explain how to generate catalog stars and galaxies and how to use them with Roman ICEM to obtain a level 1 and level 2 simulated products. I assume you already went through the installation of this software, but I will very fast go through. So in the website, you find 3 files. These 3 files are a file called YAML, which defines the environment, a file called semutis.py, which has a lot of predefined function, which I will call during the presentation of this notebook. And finally, this notebook itself, which is the simwebner.ipynb, which is a Jupyter notebook. To do the installation, just simply creates a directory, goes in the directory, and then put these files there. Then you have to download the PSFs that we're going to use. And to do this, you have to create another directory, then download them from this page, which has all the documentation by STPSF. Once you download it, you expand this file, download it, and this will create a directory which contains all the PSFs. Once you have all done, you have to create your Conda environment. So let's go back to this file that you downloaded, which is called rsim11.yaml. This file cannot be run immediately because there are a few paths that have to be defined. Unfortunately, YAML only accepts absolute path. So this means that you have to go inside and put your path in the parts that are in these three paths that are not completely defined. One is home, so you have to search for your home. And on a Unix environment, you just do echo $home and you get what you get, and you put this value inside instead of home. And then conda dir, if you have conda installed, you do conda info dash dash base, and you have the directory where it's installed, and you just put inside. When you finish editing, you can create the environment. And so you do this conda inf create -f with the name of the file. You will download a lot of things, you create your environment, then you activate the environment, and essentially at this point you can run this notebook with the JupyterLab simwebinar.ypynb. Okay. Okay, Ori has a question.
Great introduction, and I just want to underscore for everybody listening, we've said this already, but this is a great audience. We have nearly 60 people online at the moment. This is the hard part about setting up environments and software on your local machine. We completely acknowledge that. It's so important to underscore the fact that this is one of the main drivers to having the Nexus. All of these environments will be pre-configured, all of the necessary packages will be preloaded, all of the reference files will be easily accessible so that you can skip all of these steps in terms of setting up your notebook just by logging into the Nexus. So I just want to, underscore that one time while I have everybody's attention.
Yeah, that's very true. It's complicated. I try to make it simple, but it's complicated. I agree.
It's simple once you've done it a lot. I don't know how many new people, I don't know everybody on this call. There might be a lot of junior folk. And so doing this for the first time can be intimidating. And so I just wanted to acknowledge that for the audience.
So I'll say also another thing, that I made this notebook as simple as possible, in the sense I try to hide all the complexity in this file that I pass with a predefined function. So everything seems very simple, although people can be afraid anyway, but I try to make it simple as possible. So let's start with accessing the Roman data. As already mentioned, most of the stuff that we do with Roman will be on the cloud. So mostly, and this with the cloud, which essentially use Amazon services. So we are going to use some jargon here, and we'll probably have heard on newspapers recently about AWS, because there was a problem with AWS that essentially is Amazon Web Services that is used for many sites. And if I don't remember, it's 1 week ago, 2 weeks ago, there was a failure of this, and many websites were not reachable. The data that will be used on the Roman Research Networks are actually using the AWS. We also mentioned URI, which is another sequence of characters that essentially identify a resource on the internet. And you probably know the URL, which are used for websites, which are subclass of these. And finally, we're talking about S3 buckets. What are S3 buckets? Are containers, and that are used on this Amazon Simple Storage service. And for instance, the Roman Research Networks are some of these pre-done simulation, if you want, accessible. And to access them, we have to use this library, which is called S3FS. S3 is actually this S3 bucket, so it's a library to access this Amazon Web Services. What I'm going to do now is going through these cells and run them, if I can. Sorry, I have to click on them. So first of all, I will going to access the Roman Research Nexus, and there is a function what you can use, which is then ls, so essentially the list of Unix, which allows you to list all the files that are available on this particular directory. In this case, I just show the first 10, but you can go and say long list. Once you know the files that you wanna download, you will just put the URI as what I defined before, plus you add the name of the file, and you can download it. Now, these files in this particular case are in the ASTF format. So to as the one created by Roman will be. And to open these files, you have to use the Roman data models, which is imported here. And and this little example is I show you how to do it. So this is a particular command to open the file and to open with RDM, so with the Roman data models. In this case, I will show you this particular instruction that allows you to show a little bit I will run for the moment, so I can talk over as you access the stuff. So the first gives some information about the structure of the file, and also here I limited to 30 voices. So you see how this file is organized. In particular, we are watching what is in meta and what is in data. And in data, you have the data, so essentially the image. In the meta, you have other things like the WCS. There are two ways to get the WCS directly. So you get the WCS as defined in this file. Or if you want to have something more fits, kind of similar to what you have in fits, you can grab the header and transform into the fits, and then use the typical AstroPy WCS library to grab your WCS. At this point, you can simply visualize this file with Matplotlib, and you'll see that this is the simulation that has been downloaded. Okay, so the next set of data that I'm going to explore a bit is the Open Universe. In Open Universe, we had a slide before, is a collection again of simulation made with in mind two astronomical facilities. One is the Roman telescope and the other is the Rubin Observatory. And there are simulated, calibrated images. This time they are in FIT format. And again, we are going to use a similar way to do it. So we are again using the S3F. I will not reload them, but you need this S3FS stuff to go. And yeah, in this case, as I saw, maybe some of you got this notebook yesterday, and I forgot yesterday to add this AstroPy ImpIO fits library. So you need to add this line if you want to open, otherwise you may not able to open. So once you have the address of the bucket, and then in this case we have a particular image that you found that was stored there. And so I created the path that contains all this, and I opened with the simple fits open. So this should be a normal way you open a fits file, so nothing mysterious. Again, I created WCS starting from the header. And we can see this file as what's inside the file, so a science, error, and mask extensions. And also in this case, I can simply show what we got. And so this is the image that we get. And so again, this is simple Matplotlib commands, nothing very advanced. So this is what I was showing for the accessing these available images already. So that's pretty simple. And the same command will be available on the Nexus when it's available. So we will not need to download images on your computer, but if you're working on the Nexus, you will be able to work all in the cloud and import in the cloud these images, which, you know, if you have many images, is very advantageous. Okay, let's now go to the next part of this notebook, which essentially consists of generating catalog of sources that we'll need for creating these simulations. As you probably know, Roman, you use the Gaia stars, the Gaia catalog, to correct the astrometry of the images. So since he has a very big field of view, there are several Gaia sources that are going to be found in any of the images taken with the WFI. This will be exploited to improve the astrometry, since the Gaia sources are known with really exquisite accuracy. So to do a simulation which really similar to what we'll see in the sky, we can also add Gaia sources to our simulation. And this is the way to do it. So we have a way to call the Gaia archive and download a list of sources. I will not run this cell in particular because it takes a lot of time, because it depends on the archive, and I don't even know how many minutes it'll take. So in the interest of time, I will skip this. You can do it. And I'll skip also the next one, which allows you to write the catalog on your laptop. But I go to the third one, where I already did the two previous passages. I can just open what I said before, and I can see what is in this catalog. So in this case, I just show the first 5 lines of this catalog. So we'll see, we can explore what we find here. So we find different sources and in different filters. Once I have this, I can also show, I wrote a little script that is called plot stars, that allows you to plot the sources in this catalog with their coordinates on the sky. So this is a particularly a part of the sky which has not so many stars, because actually I purposely chose a part of the Lockman Hole so it's not so crowded. So you see a lot of stars, but not so many as in many other parts. You can, if you have particular needs to simulate parts of the sky with a lot of stars, you can simulate stars, and this is the way to do it with Romanized Sim. So with Romanized Sim, we can get these functions, especially catalog, which is going to produce a catalog of sources. And we can make a catalog of stars like that. We can explore what is here. And we see again similar things to what we had before. I forgot to mention that in the routine that I mentioned before, so for Gaia, this Gaia stars that I put together in your simultaneous.py file. This routine contains also a step where the Gaia catalog is read and put in the format that is readable by Romanized Sim. So you'll see that as very similar as format as this other one that is created by Romanized Sim itself. In this case, also notice one thing. I have a type called PSF here, which means this is a catalog of stars, and Romanized Sim will understand this is a catalog of stars, so use the PSF to generate point sources. Again, I can use plot stars to show you the catalog that I just created. Finally, you can create a catalog of galaxies using essentially Gaussian through Romanized Sim. And so that's slightly more complicated. You can put a faint limit, you can put the half-light radius that you want, the bands that you want to simulate, and again, you can call catalog with make galaxies, and this will generate a catalog. Yeah, this doesn't take so much time, so I can run, and this also writes your catalog down. And in this case, I can reread, not very useful, but and show you the catalog that comes out. In this case, you see this SER, which shows that these are not point sources, but galaxies. And you see there's also have other fields here, half-light radius, PA and BA. BA is the ratio between the axes. and pi is the angle of the axis, and that defines essentially an ellipse. And I wrote a little other one, a little script that does plot galaxies. In this case, it takes into account the fact that we have ellipses, so it can show you the ellipses and the half-light radius, and a flux and the color, which color coded by flux. Okay. It's interesting now, since you are doing simulation with for the WFI, to show what WFI appear, how the WFI appear on the sky. So in the SimMaterials, there are two things. One is the point Wi-Fi. So it's a class that allows you to define the Wi-Fi position and position angle. And the other is plot Wi-Fi that allows you to plot this on the screen, and also to show, if you want to put label equal true, which detector is, to essentially label every detector with their own number. So if I do this, it'll show you that with this particular position and rotation angle 0, the detector appears like that, and you see the numbers have some logic, but they are not immediately recognizable. So it's good sometimes to plot and see which, if you are simulating a particular detector, knowing where this detector is located. We can also grab the catalog of, for instance, of galaxies that I did before, and plot this Wi-Fi footprint, for instance, using a dithering. So to use a dithering, we can just add an offset to the position we define. So that's the way to do it. We'll do a loop, and we'll do offsets that are defined here, X offs and Y offs. And I define different colors also, just to be a little more clear, even it will be confusing anyway. So when I run this, we'll see that this plots the galaxies that I showed before and the detector with 4 different colors, which corresponds to the 4 different positions. And the detector is essentially the same orientation, so the same center and the same angle. This can be useful if you are going to do some simulation, just to see if you actually are catching the stars or the galaxy that you think in your catalog. Now, once you have these catalogs, you wanna, for instance, put together the catalog of stars and the catalog galaxy that you created to run a simulation. In this particular case, I will put together the Gaia catalog, so the Gaia sources and the galaxies that I created in this full catalog file. And if I run full catalog, and I will not limit at this point the number of sources, I will say that the first one are the galaxies that are identified by this SIR type, and the second one are the point sources that are defined by the PSF label. Once we have these catalogs, you can finally run the simulations with the Roman IC. So we are going to do simulation of single images. So what Roman IC does is simulates images for each detector separately. There are a few caveats here. Roman IC use the CRDS files that you give, and we actually define them at the beginning. So these are the reference data files, which contain all the instrument things like floods and bias and whatever. But you can also use with no reference files, but this is not recommended because it will not really be an accurate simulation of the data. There are things that are not simulated. For instance, there is the effect of 1/f noise. And it's possible also to add the multi-accumulation tables. You can read more in detail about multi-accumulation tables in the Roman APT User's Guide. And if you're really interested in particular observations, for instance, I didn't mention at the beginning, but for instance, if you observe fields which have very bright sources, you probably want to choose MA tables that have a lot of points at the beginning of the ramp, because you're sure that most of the ramps will be saturated. So there will be no more linear in the ends of the ramp. So that could be a case where you want to have a slightly different MA table. You will be able to put a time observation. For instance, now we put as a time the first day of launching space of Roman, which we hope will be the end of September, whatever it is, next year. And so, okay, so what we'll get at the end, if you run the simulation, we have this underscore uncall SDF. That's if you run for L1 cubes, essentially for L1 ramp cubes. Or you have other things that are calibrated files if you run for level 2 files. So here again, I don't want to scare people, so I put a lot of this preparation for running Roman sim in this file that is called simutist.py that we are going to call, and I define routines called run Roman sim. Nevertheless, we have to pass to this Roman sim a few things. So we have to give the center of the simulation. You have to give the catalog that we created, and we have to give a few things. So this is the first. So this is the detector, and it's called SCA, which stands for Sensor Chip Assembly. And this is the way that is called by the engineers, but we can call just the number of the detector. Then we have the optical element, which is the filter we want to simulate. For instance, in this case, I chose the filter 106. Then the number of the MA table that I talked about before. So this table that specifies how the reads are grouped in the ramps. And then one name that you can give, and one C that is used by GalSim to simulate the galaxies. The level of the simulation is shown here. In this case, we run a simulation, and around the simulation, so I talked. It takes a little bit, and this simulation it says, oh, we're going to do this this filter, and give some infos. And actually, I suppressed a lot of the infos in this run Roman sim. But if you go into the file, you can actually change a little bit and see many information that comes out when you run the pipeline. So this Roman sim. Yes, I say that I'm going to do level 2. So we are going to the different parts. So you see portion electrons to resultants, etc., etc. So he's giving the different steps where he is now. And eventually, when this is finished, we'll be able to show this image. Okay, so there is a little few. Now, since we did simulate level 2, you can see there is a step saying fitting ramps. As I said before, the level 1 is simulated first, and then level 2 is just fitting the ramps and giving the flux. And so we have now the simulation is complete. The simulation is complete. We have our file, which will be, since we call it single, this is the first detector, and this is our filter. So we can now see, I put here a little bit of things. I'll explain in a moment as they run. So this grabs the file that's been created. You see there's a lot of instrumental effects here are visible. And on the top of this file, I put also the Gaia sources that are in this field, which has been simulated. You can see them with little green circles that are around the simulated images. So that's essentially the way you do to simulate things. You can have simulations in a more complicated way, as I showed before. We can do, for instance, a simulation which include dithering. So, and this will be useful if you are going later to use the pipeline. So you're going to use these different images and mosaic them in a single image with the Roman pipeline. So in this case, I'm showing you what I'm going to simulate. So this is our catalogs. I put on the bottom the catalog of galaxies, the catalog of stars, Gaia stars, and 4 dithering position for the WFI. So I will not going to run this because it would take a little bit more time, but it runs essentially in the same way as the previous. The only trick I did here is to go in and put all the simulation and center in the first detector. So to do this, you have to use the PySciF. So this library that essentially gives us the information about the WFI. And you have to define the position you are centering, you're essentially directing the observation. And from that, you can find the center of a particular detector. So in this case, we get the WFI01. We are going to use this to define our pointing. So at this point, with the points, with the Sierra DEC in this particular part, and we are going to do this simulation. I think this was using exactly the same stuff, and you can see that the WFI1, which is this particular detector, is centered on the center of the field. So that's what the simulation does. And after you run the simulation, you can see, for instance, one of these fields that is similar to this before. In this case, I just put the circle of the stars as blue circles. Pardon. Okay, so we are at the end of this notebook, but you can do much more. And I put this little paragraph, this little section to this notebook, which says beyond this notebook. So clearly, if you are going to do a lot of simulations, you want to go slightly faster and you want to do multiprocessing. So, but this depends also on the power of your computer, or if you're going on the Nexus, you're probably going to use in the future, sorry, you're going to use some accounts where you can have many processors. So you can find an example how to run Dusk, for instance, and to use Dusk to run this simulation in this notebook that I linked here. Then, as I said, all the level 1 and level 2 products that are generated with this Romanizing package are processable with a pipeline or Roman, which is called Roman Cal. And here you can find the link to the Roman pipeline. In particular, you can find 2 notebooks at the end, which shows you how to do a reduction of one single level 1 product to obtain the level 2, or another notebook which says how to mosaic different level 2 products. So once you have different level 2 images, you can use this Roman Cal with this particular notebook and see how to obtain a complete image. And I think I will stop here.
Okay, great. Thank you, Dario. And thanks for everyone's attention. That was a lot, but now you can run Roman ISIM. Okay, so we do have a couple questions. Vivian, do you want to read them off?
Yeah, they're
And
actually a lot. I'm not sure we can get through them, but maybe I'll
yeah, we'll
start from the
see.
top.
I can stay a little late, and specifically for the people who asked the questions, if you want to stay on, you can. Dario, can you stay a few extra minutes?
Sure.
Okay, great.
All right, so the first question was, is the footprint of Roman a default when downloading the Gaia sources?
Pardon, so is the footprint?
Of Roman a default when downloading the Gaia sources?
Okay, you download Gaia sources in a field with the center and a radius. So you actually don't download the footprint. You download something that you can use then. So usually you get something which is at least a half-degree radius.
Great. There's a question about simulations based on galaxy number density, but that's answered on the chat, so I'll skip over it for now. How similar is the simulated level 2 processes to what the Roman pipeline will do?
Okay, so the Roman pipeline has different possibilities. So what is used in a Romanized sim is essentially the default reduction. You can use different things, like for instance, different kernels, different things. And if you're really a power user, you want to go through this. Also, as Ori was mentioning before, it's also a possibility to learn how to use Roman Call.
Thank you. Are the coordinates input to run Roman ISIM the center of that detector or the mosaic of them?
Okay, so I show an example where you can put the center, for instance, on one specific detector. And depends on what you do. But essentially, yes, it's the center of the aperture, which is more or less situated here. It's in not exactly in the center of the array, but slightly moved. But that will be the typical center.
Great. And I think there's a question about how long it takes to download the files. And I think that that you did pre-run things beforehand, so that that's solved.
Yeah, the downloading of Gaia is in the order of minutes, so I didn't want to spend minutes waiting.
Okay. There's also a question about similar Python script for simulating GRISM observation that got also answered on the chat itself. And then about Roman's data model. Are you going to go through Roman's data model?
The Roman data models are essentially a library to read HDF files and other catalogs, and it's essentially a library that simplified the reading. You can read, for instance, if you want an HDF file, you can use HDF and read it, but it'll be slightly more complicated. So you have to go through different steps, and Roman data models simplify this because it's already a lot of things defined. It knows what it's reading.
Okay, great, thank you. I think those are all the questions that were not covered by the chat itself, but Ori,
I
you
just want to
can-
add one thing about the downloading of the data. A lot of these reference files are just that, reference files. So once you've downloaded them once, you don't have to download them again. It checks to see if they're in your download directory. And again, this is the beauty of the Nexus. You won't have to download those files. So anyway, I just want to make that clear that every time you run a simulation, you don't have to go through that download process.
Yeah, this is probably one thing I skipped, is that when you run Roman ISIM, the system will download in a cache directory a few files that are reference files, and it will download the specific detector. So if you run for another detector, it will download another series of files. So yeah, that takes a little bit of time. I see a lot of
There's one last question that came through, it looks like. Vivian.
flashing stuff. I cannot read.
in the final yellowish RA deck output image that you showed, why are we seeing circular patches? Like a layer of the screen has been wiped with a cloth in the first column of image. Is it related to detector surface itself, or is it because of data clearing and analysis process done?
That's what is in the detectors. Probably the fact that there are for the reduction, they are using slightly different reference files, I think. So this kind of peculiarity of the of the detector are not completely correct, if I'm not wrong. But also it's a very, 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 a very low level. So you can see all the context is very high.
Okay, I think that's all the questions. Sorry if you want to wrap up.
Well, I hope everyone found that useful and entertaining. I just want to close out by saying to make sure that you've joined our mailing list and that you're prepared to attend our next webinar. I'm just going to advertise that quickly here, which is going to be December 2nd, Tuesday at 2 p.m., where we will be discussing the Astronomer's Proposal Tool, APT, which is the tool that you used if you have written HST or JWST proposals. But in this case, the tool will be specifically used to either design new surveys with Roman, if that's something you want to do, or explore existing core community surveys with Roman on Roman. And we're going to show you a little bit more on how to do that as well. So tune in Tuesday, December 2nd at 1 o'clock Eastern. And thank you everyone for your time.